In this video, I'll be looking at some questions from Unit 8, Worksheet 3. We're going to start with number 2. This one is a little tricky because the mass of the grinding wheel is not given. So it says a large grinding wheel, oops, hang on, my Apple Pencil is not behaving. So it says a large grinding wheel in the shape of a solid cylinder of radius 0.33 meters is free to rotate on a frictionless vertical axle. The wheel spins at 2 revolutions per second. So in order to solve this, first I'm going to sort of picture it. So it's a wheel, and it's rotating on a vertical axle. So it's helpful to be able to draw that. They give us the radius. The radius is 0.330 meters. And it's spinning at 2 revolutions per second. So 2 revolutions is 4 pi radians per second. And that is my angular speed. Okay, so it says a friction force of 250 newtons is applied to the edge of the wheel, causing it to slow down. Calculate the net torque. So we are assuming that this frictional force, let's say the wheel is rotating this way. The friction force is going to oppose motion, so we would have a force of kinetic friction like that. And they tell us that the force of friction is 250 newtons. And again, that's opposing the motion of the wheel. So I know that torque is equal to Fr times the sine of the angle. The angle between the force and the radius at that point is a right angle. So it'll be the sine of 90, which is 1. So the torque is going to be 250 newtons times 0.330 meters, which is 82.5 Newton meters. And remember, that's not joules, that's Newton meters. Okay, then we have to calculate the moment of inertia of the wheel. And the moment of inertia of a disc or a cylinder is 1/2 mr squared. And here's where we run into a problem. Mass is not given. So we're going to have to give the answer in terms of whatever the unknown mass is. So I can't plug in anything for m. So my answer is actually 0.0545 m, so times m, and then the units on that are kilogram meters squared, assuming that mass is measured in kilograms. Okay, let's see if I can, there we go. Calculate the angular acceleration of the wheel. So we know that Newton's second law for rotating systems is that torque equals moment of inertia times angular acceleration. Remember, that was analogous to F equals ma. Force is like torque, mass is like moment of inertia, and acceleration, we've got centripetal acceleration and angular acceleration. So I have the torque, and I have the moment of inertia, so I'm just going to divide. So I'm going to take torque divided by moment of inertia, so that is going to be 82.5 divided by 0.0545 m. And when I solve that, I get 1,514 over m, whatever the mass is. And the unit for that would be radians per second squared. And I should probably make that negative because I know this wheel is going to be slowing down. Okay, finally, it's asking me how long will it take the wheel to come to rest. So let's see. So the initial speed of the wheel we determined here is 4 pi radians per second, which, by the way, let's see, 4 pi I think is 12.56 radians per second. And the final speed of the wheel is going to be 0. And we know that the angular acceleration is negative 1514 over m. And we would like to find delta t. So I'm going to use the formula final speed equals initial speed plus acceleration times time. Or I could rewrite this as acceleration equals final minus initial over Actually, I'm going to solve it for t. So it would be delta t equals final minus initial over angular acceleration. So the change in speed would be the final, that's 0, minus the initial, that's 4 pi, or 12.56, over the angular acceleration, which is negative 1514 over m, and then I would simplify that. So when I simplify that, I end up with 4 pi times m over 1514, and that would be seconds. It also corresponds to 0.0083 m. Okay. Let's look at one more. Let's look at the next one, number 3. 2 wheels with fixed hubs, each having a mass of 1 kilogram. I'm peeking at my answer key here. Start from rest, and forces are applied. 1 Newton to the first wheel, and F2 to the second wheel. Assume the hubs and the spokes are massless, so that the moment of inertia about the center of mass is just mr squared. How large must the force F2 be to impart an identical angular acceleration on the wheel? Okay, so what we're trying to say here, or what we're trying to figure out, is when is the angular acceleration of the small wheel equal to the angular acceleration of the large wheel? And we know that angular acceleration is equal to torque over moment of inertia. Oops, that should be large. Okay, so torque is equal to force times radius. And the moment of inertia of the wheel is mr squared. And I'll do the same thing for the large wheel. And then I'm going to simplify this. So one of the radii cancels. And so what do I have here? I have the force over the mass times the radius equals the force over the mass times the radius. And in this problem, we have that the force on the small wheel is 1, and the mass is 1, and the radius is 0.5. So this side here would be 1 over 0.5, or 2. And so on the other side, I've got that the mass is 1 and the radius is 1, and I want the force to come out to the same ratio, so this force has to be 2 because 1 over 0.5 would equal 2 over 1, so this force would be 2 newtons. Okay, I hope that helps. Please keep your questions coming, and I will do my best to answer them. Thanks very much for participating in this class.